It's really a pleasure to be here after like 1 year. I was here last year to give a talk on chiral magnetic effect, but I was downstairs in the other room. So in this talk, I think what Jiang Yang told me to give an overview of these isobar collisions that happened in 2018 at the relativistic Hebbian collider, which is over here, not easy to see. And the data were collected by the star detector. And I'm going to just give you an overview of the experimental opportunities with that isobar run at RHIC. So this is going to be a little bit of general introduction for the mostly to kind of people, so that you know I can introduce you to also to the people who are not from our community. So I'll briefly introduce our field and the isobar collisions at RHIC. And then I would like to argue that this kind of provided us to precision measurement that we were not doing in that sense, like the precision that we achieved, or like was never been achieved before in some of the observables. So it's an excellent tool. And then, you know, I think that's the most important relevant topic for this workshop, that it provides us a way to understand nuclear shape and structure. And then actually the main reason for doing this collision was to study strong field effect, like magnetic field driven effect. And that are photon induced effect, chiral magnetic effect. I don't think I'll be able to go to polarization. And then there is an interesting development. This recently we realized this can also tell us, you know, provides us insight to understand the structure of baryon inside the baryon. And that's actually like interesting and deeper questions that we could address with the isobar collisions. That's very recent development. So let me see how far I can go with this. Okay, so actually, I don't know, I mean, how to say that when this thing started. I mean, maybe what we are doing now goes back to when Rutherford tried to scatter 1 alpha with the nucleus a long time ago. We have been doing this for a long time. You can see that the only difference that is happening is that the energy of the objects that we are colliding with each other, it was like very low energy alpha. But once you kind of increase the energy, you start to do, you know, get other going to the domain of nuclear reaction. So this was existence of nucleus. And I think at some point of time, what we are now doing is we are going to collide a relativistic object with the other. So here it's intrinsically different from lower energy reactions. Most of the time, what will happen is that if the energies are really fast, the valence degrees of freedom mostly pass through each other. And what you have is like a field, and the degrees of freedom we are producing were not there actually. It's just like coming out from the underlying field. And this way provides this kind of provides us to understand the building block of strong interaction, the underlying field theory. The time scales of this lifetime of these things are of the order of like Fermi. So several differences. I mean, I could go back to this later on. If nucleus is at rest, it would be something like this, a collection of nucleons. But once you boost it, what happens is that the degrees of freedom that are important are dominated by these short-lived degrees of freedom. So you could think of like this is like a saturated gluonic object. And so far we know that if you want to describe the data in Hebbian collisions and kind of a model, an approach based on very strong color field that is produced, and they collide, and then basically there is a formation of an intermediate pre-equilibrium stage, and then it evolves hydrodynamically and hadronizes. So this kind of modeling, based on the fact that you produce very strong color field at the early stages of collisions, and that kind of has been very successful. So this is the one important difference of colliding objects at very lower energy versus what we are doing now. What we do. The information of these early stages are somehow, deep inside the profile of the particles that we detect. So it's actually becomes difficult to get back here, but there are ways where we can actually understand what exactly collided. This is the first important thing. So this was creation of very strong color field in these collisions. Second thing is that these collisions provide very strong electromagnetic field, which is of the order of 10 to the 18 Gauss. And the reason is because two ions can be thought of two wires carrying current in the opposite direction. These are relativistic objects, so the strength of the magnetic field is enormous. So, and you could compare to like what is, the strength of magnetic field of Earth, our detectors, or I don't know actually the number here, but I think it's wrong here, but this is one of the strongest ever, magnetic field, electromagnetic field produced in the universe. So all of these provides us exciting opportunities to study physics that we could have not done before. This is our detector. This is our star detector, and that's where we are. I'm going to mostly discuss the results from the data that are collected by this. So there are many systems. I don't want to go into the details, but the important thing of this detector that which analyzed the isobar data was that it has this wide acceptance over which it can detect a lot of different hadrons and measure bulk properties. Actually, that's what the specialization of this detector, and also identify different kind of hadrons. And one event would look something like this. I don't know why it's not moving. One collision would look something like this. This is our central barrel, and these are all different tracks. So here the gold and gold ion collided. And there are detectors in the forward, and then there are detectors in the center. The central detector gives us quantities like momentum, charge, particle identification. The forward ones help us trigger a collision and provides us things like the direction of the magnetic field, which I'll explain later. The most important thing for non-experts in this room is that I think there's something that I must tell you about heavy ion collisions. That is the elliptic anisotropy of the particle production. Since this is the first talk, and let me introduce it. Every time, so what I'm showing you here is a picture of one event. You see the part of the detector that I showed you before, but we are looking from this side now. In every collision, we can find out the direction, where you will have something like 0 to 8% more particles emitted. There's a preferential emission of tracks going in that direction compared to the perpendicular direction, which is like 0 to 8% less. So this is the most dominant anisotropy of particle production. This happens in every event, actually, more or less within this range. And this axis is the axis of elliptic anisotropy. I call it psi 2. And then the strength of this anisotropy is measured through this cosine of this angular distribution. Like this is the plane, and this is the angle of a given particle. This is the cosine of that. So that's what we identify. And the reason why this is elliptic shape is because of the overlap of the two nucleus. When the two nucleus, two nuclei overlap, there is an elliptic zone in spatial coordinate that gets converted into the momentum anisotropy. There's one more thing here. This direction of the ellipse, actually the minor axis here or major axis here, also aligns with the magnetic field direction, because that's how the geometry is kind of, you can see charges are distributed, the field is distributed like this. So this kind of is going to be important for what I'm going to say, but not precisely. Yeah, there is a efficiency to this. So this correlation of magnetic field and the axis, and the efficiency is maximum in the mid-central collisions. I will explain what is mid-central in the next slide. I will define everything as I go on for the non-experts. But that's not only the thing. That was like a very, I don't know, it's a very ideal picture of two nucleus, like two smooth sphere or something. In real life, the nucleus is, each nucleus is made out of these nucleons, and their positions are random. So there's a lot of fluctuations. So the overlap zone is not ellipse, but it could be like anything. And that you can have a triangular shape, you can have, other shapes. And that is also kind of, propagated to the distribution. So for example, you can identify an axis of triangularity. Basically, you can decompose in Fourier harmonics and you get all the orders, actually, whatever you measure. And the reason is this fluctuating geometry of the initial state. So now you can actually see that when the two nuclei will overlap, exactly like in the very central collision, which I will define later, it will be interesting to see what is the shape, because then it will be like almost spherical. And if the nuclei are intrinsically deformed, that will also show up somewhere. We expect it to show up in the measured distribution. And a very important thing, that very important terminology that will be used in this workshop is the centrality of collision. And we try to make best use of this. When the impact parameter is 0, like fully overlap, mostly what happens, we call it central collisions, and mostly strong processes dominate. And you can see here, right? If the nuclei, right, if the nucleus, like two nucleus are like spherical, the anisotropy, you expect it to be, symmetric, right? Symmetric anisotropy, unless there is fluctuations and deformation. And that is the key to study nuclear deformation, which I will discuss later. As you change the impact parameter, the impact parameter increases, we call it peripheral. Still strong processes dominate, but you see that the number of tracks are less, and these mid-central, or like between these two events, are very important to measure all this magnetic field-driven effect, because now we have better efficiency to find the direction of the magnetic field. There's one more interesting thing. When the two nuclei, the two nuclei, the impact parameter is very large. So you have a near-miss collision. The field, the photon field from one nucleus can interact with the gluon, or the photon field from one interacts with the other, and we call them multi-peripheral collisions, or the electromagnetic field dominate. Still particles are produced. We can use that to do a tomography, actually characterize the gluon distribution inside the nucleus. Okay, isobar collisions. When we wanted to do it, we were looking at these charts of nuclides, you can see here, and we're trying to find a pair for which, of course, isobars means like the proton numbers are going to be different, or the neutron numbers are going to be different, but the mass number is going to be same. We're looking for the easily available one, also the one for which we can get some difference in the charge, electric charge, so that we can get some difference in the magnetic field. So zirconium has this less proton, the ruthenium has these 4 extra protons, so the magnetic field is higher in this collision than this. And this is actually the projected magnetic field with centrality. And this is what I think Uli was referring to, that you can see that the efficiency is best, correlation is strongest in mid-central event, but for ruthenium collision, it's a little bit higher than zirconium. And that's like 10 to 15% larger. So any phenomenon that depends on magnetic field we expect it to be larger in ruthenium and zirconium. But the advantage is that everything else, non-magnetic field effect, whatever you can call it, those are going to be expected to be similar. So that was the idea. That's why we ran isobars. We collected like approximately, as you can see, 3 billion events for each of these. Actually, actually like 2 billion, something like 2 billion for each of these species over this month. And we switch the collisions, like flip them every 20 hours. To just remove the systematics, like any kind of detector effect or any kind of experimental effect is going to be distributed evenly between the two species. So at the end of the day, you measure an observable in ruthenium or zirconium, it's going to be expected to be different from one. But the important thing is the precision is going to be very high because the systematics gets cancelled as much as possible. Yes, please.
Did you do any mixed collision?
Oh, no, we didn't, because I think if we realized everything we could achieve with the mixed collision, we can just achieve by mixing the data sets pretty much for the purposes of the observable we are measuring. So this was the idea. Originally, this is supposed to be an observable sensitive to magnetic fields, but you can do any observable. And if there is some effect, you could get a very high precision. That's the idea. Okay. And this was like a journey from 2018. We did go to like 2021 when we published the first result. And all the analysis that came from, all the results that came from the analysis were outcome of a blind kind of procedure to make that, to get rid of any kind of bias or heuristic in the method. So this is practically like very precise and I think a great achievement from the RHIC program. First exciting result. So let me move on to the first topic. How am I doing on time? Oh my God, 15. Okay. So first thing as the nuclears say. First thing we measured is the number of tracks as a function of the violence of the collision, centrality, right? So this is the peripheral miss, near mist or something, and this is most violent. And you cannot see anything in the upper panel where I plot ruthenium on solid and zirconium on open square. But here in the ratio, you can see these are very precise, the measurements are very precise, error bars are within the marker size. You see there is a difference between the multiplicity, right? The number of tracks. And why this was happening, one of the possible explanation, we could kind of find out is that the ruthenium is smaller than zirconium. Simple way, okay? There are more complicated, there are details to that statement that I just made. So this is smaller, at the same energy, you have more density, energy density. So this produces more number of particles than the other one. So that's very nice. And actually, you could go a little bit deeper, like why it's bigger, it's because the neutron skin, or I will get back to that. Yes.
How do you define centrality experimentally?
Oh, okay. Okay, that's the next slide.
Wait,
Sorry. Yeah, please.
this slide first. This kind of ruthenium is large.
Right, yeah.
So why is it more multiplicity?
Actually, you have to this R is large, but this is more like this one. Did I type it wrong?
Yeah, there's a.
Oh, okay. So I might have typed it wrong.
Oh, okay.
Okay, let me just check that. Yeah, I think I might. There's maybe a typo. Yeah.
But the 8 on this, right? The internal percentage is.
This is so okay. I think I know. So it's okay. So the R is smaller for zirconium, but what happens is this diffuseness, which is the neutron, that's smaller. Okay. So there's no typo. Okay, sorry. Let me get back to that.
Can I ask you a question?
Sure.
So what exactly is R here and how did you get that?
This is the actually in the Wood-Sachs and distribution. No, we get it from, this is from a density function of theoretical equation.
It's theoretical that.
This is just the rate, yeah, theoretical one. Okay. You had a question, right?
My question is similar.
Oh, I see. How do we define centrality of collisions? What we look at is the probability distribution of number of tracks. Okay, so this is probability, and that's number of tracks, and this black histogram, which is a little bit below here at lowest multiplicity, that's the data. Okay, over here, and then these two different curves are different kinds of Glover model calculations with various Wood-Sachs parameters, and we try to fit this our data with this Glover model, and then from that. In the Glover model, we have the information of the geometry of the impact parameter. From that, we can figure out how violent it was. So that's how we determine centrality from a data model fit. I think that was the question, right? And there is also loss of trigger. It's loss of trigger efficiency in the peripheral event that is recovered by the model. But the interesting thing is that the best fit was obtained from this kind of density functional theoretical equation, which predicted that the overall the diffused area or the size of ruthenium is smaller than the zirconium. So zirconium has bigger neutron skin, right? It's wider spread, and that's actually in this plot is difficult to see, but once you make ratio of the distribution, so this is the this is the data, the gray. And this is one case, one of the Glover case where it doesn't have the neutron skin. It has the same kind of diffuseness parameter that doesn't describe the data, but the one in which this is more diffused, that one, that kind of describes the data here. So it tells us that
So is there any difference between the two track distributions of the two filters?
track distribution. There is difference between the track number probability distribution of tracks. There is. That's what this ratio is. Right? It will be 1 if there's no difference. So this shape is because the underlying distribution is different. Is that what you're asking? Sorry. Go ahead.
So this analysis somehow seems to assume that multiplicity and impact parameter are one-to-one correlated, and there are no other fluctuations in multiplicity in a given impact parameter that can interfere with this interpretation.
So actually, no, actually, it assumes that even at a given impact parameter, the nucleon positions are fluctuating, right? Because given the Saxon distribution, and also even if there is just collision between two nucleons, like a PP case, at the same impact parameter, there's an underlying fluctuations which is like negative binomial. So those are incorporated in the model to describe the data. Without those, we will not be able to describe. Actually, it will be much that it will not be, the model will not be wide enough to describe the data.
But Bill is right. I mean, when you plot impact parameter against multiplicity, there is a very strong correlation, and that allows you to translate this into geometry.
See, only 7 minutes? Not even. Okay.
There's a 10 minutes to actually.
So anyway, I described this. There are more detailed density functional theory calculations that were later on compared with the data of multiplicity ratio, and then there is another thing, the net electric charge stopping that means rapidity, and that kind of is consistent with the fact that zirconium has thicker neutron spin. Finally, we did this a lot of systematics of the elliptic anisotropy by taking a particle in our detector angular, the angle of particle, and then the event plane. So these are elliptic anisotropy, but there is a gap between how you take the event plane and the particle, or like a rapidity gap. And so just for the moment, ignore these systematics, concentrate on the most central event here where all these different measurements agree. And if you take ratio here between ruthenium and zirconium, this is above 1. And this greater than 1 ratio in most central collisions, you cannot just explain by the fact, just some kind of fluctuations. This has to be because of the fact that the ruthenium, I think one of the most probable explanation is that the ruthenium has larger beta 2 quadruple deformation than zirconium. When you measure triangular anisotropy, like just triangular shape, you see the opposite. Ruthenium has less triangularity than zirconium in the central events. And this is explained by the fact that you have larger beta 3 in zirconium. Okay. That is also another thing is that you measure the transverse momentum, mean transverse momentum. This is defined by transverse momentum of one track with respect to average and the fluctuation of it. And that you also see when you do between ruthenium and zirconium, that also fluctuates and it's not 1. So let me try to show you by the cartoon. Imagine the nucleus have no shape, like spherical. You collide them and you have most violent collision, like central collisions. If there is no preferred direction, nothing kind of changes. It will fluctuate orient differently, but there's no kind of special direct anisotropy. But if you have large prolet deformation, there will be a preference of how they collide. And this actually goes back to a long, many papers, many years ago. But the interesting thing is that when there is a large deformation along this axis, elliptic deformation, the overlap area is bigger, so the density is lower. So large anisotropy is associated with low transverse momentum. And then the opposite, right? When you have small anisotropy, large transverse momentum. So you already see this. By the way, there is one more thing. This configuration is rare than this, okay? Because you can see just by orientation. So you will expect definitely that if you have ruthenium here, that is more prolate than this elliptic anisotropy will be larger. But the transverse momentum, which also fluctuates because of this, that will be more in this case compared to any non-deformed nucleus. So that's why we see this and it kind of is consistent. So that was the summary. Let me quickly, I don't know, 10 minutes?
No, we have 10 minutes for discussion, but
Okay,
if you
okay,
want to
so
cut into discussion. then
Okay.
spend a few more minutes.
Let me go back to the main important reason why we collided isobar. The isobars are collided so that ruthenium generates more magnetic field than zirconium collisions, right? It's a little bit higher, 10 to 15%, but it's magnetic field square as a function of centrality. So we should be able to see this effect in something that is sensitive to magnetic field. First thing, okay, it's not in chronologically, this is not the first result that came out of STAR, but here is a demonstration of that we are in the right. Like actually, I think there will be more discussion on this. We are looking at a collision where you miss, basically near miss, or okay, it's not near miss, but we are looking at collisions where the field, the electric field of one interacts with the electric field. So basically, photon from one interacts with the photon from the other and produces E plus E minus. Just two photons going to plus E minus. This is called Bright-Wheeler. And you can see the process should go as the atomic number, C power 4. So if you have ruthenium over zirconium, you should see this ratio. This is systematic, like 44/40. And this is what was actually measured. E plus E minus, what happened is that, I think, yeah, here you can see the data. I'm just showing already the yield of this E plus E minus pair production in ruthenium over zirconium as a function of the transverse momentum of this pair. So this blue line is this Z power 4 scaling that you expect between ruthenium and zirconium. We have the data points here, and this green one includes more corrections like QED effects, more involved calculation. So you see at the low momentum, the data points are going above. I mean, the significance is not enough, but this is in the right direction. So at least we did collide really ruthenium and zirconium, and you see some effects that are consistent in the right direction. Now, what we wanted to do mainly was to study something called the chiral magnetic effect, and that happens because when you have collisions like this, in these collisions, what happened? The mass of the quarks, which is generated through the interaction, with a chiral condensate, pretty much like how you get massive quarks in Higgs, but this is the most dominant mass. This gets turned off if you have like a production of like a quark-gluon plasma, or in these collisions you expect that to happen. So in QCD Lagrangian, you kind of don't have this term, but then you can have, so the chiral symmetry is restored, but then you have these other terms which can break this U1 symmetry and left and right hand symmetry, and that in the presence of strong magnetic field lead to a current, electric current along magnetic field. This doesn't happen in physics normally. Electric current along magnetic field. This violates parity. So this is called chiral magnetic effect, and that like happens because first you have deconfined medium, and then you have this imbalance magnetic field, and then finally so this is what we wanted to study. But for this you need to find the magnetic field direction which is perpendicular. And this time you need to see that the positive electric charge is going along B and then the negative going in the opposite. That's the current. We measured it using this variable. Okay. But there is a background process that mimics it. So this is why we need isobar. Because in isobar we expected this will be same between ruthenium and zirconium, but this will be different because the magnetic field strength is different. When we measured our observable in ruthenium over zirconium, this is the ratio. Different blind analysis group, different groups, they didn't know each other, all different results that you see. This is 1. This was supposed to be greater than 1 if there was this effect, but with the data points are below 1. And the reason why it's below 1 is, we expect it to be greater than 1 for this phenomenon of chiral magnetic effect, but just below 1 because the multiplicity dilution, which was multiplicity was larger in ruthenium. Anyway, so if we put all the numbers, the amount of signal that we expected from this, collisions, given a realistic magnetic field difference will be limited to something. You could see the numbers are like 5–6% over here, and so we kind of constrain this phenomenon. In last 3 minutes, 2 minutes.
Yeah, go ahead.
Okay, I'm gonna quickly tell you something exciting. I don't have time for this. Question is that what exactly carries the baryon number? So baryons are made of 3 quarks, and the idea is that the quarks are carrying the baryon number, right? And if this is true, there will be some problem. But that was realized by these people here a long time ago, actually. Imagine you have collisions of 2 nucleus, and these are the valence quarks, right? If the valence quarks were carrying baryon number, we shouldn't be able to stop them at the central rapidity of our detectors or measurement. This is our detector. One beam is going this way, another is going this way. Valence quarks are not going to be stopping here. We should see them over here near the fragmentation, but we see a lot of net baryon here at the central rapidity. And the reason is simple. The valence quarks carry a lot more momentum, so their wave function in space is more localized. But this is like strips are valence quarks, but the gluons are more fat. Okay, so they kind of interact a lot, but the valence quarks should pass along the light cone or something like that. Shouldn't be here, should be here. There's not enough time to stop them, but we see a lot of them stop. So in these papers, it was proposed that the flow of the baryon number is not along the flow of the valence quarks, but at the center of the baryon, where you have this junction made of gluons. Can we prove it? That the baryon number really flows along this, not along this quarks, but at the center. And this is where isobar actually helps. I'm really running out of time. So if quarks carry baryon number, you need, in order to stop a baryon, you need to stop all of them together. So what will happen is quarks carry electric charge, we know that. So there will be a mismatch between the amount of electric charge you stop and the amount of baryon you stop in this picture when the valence quarks carry. But if it is carried by a junction made of gluons, gluons are easier to stop. So you will see again kind of similar amount of or a different behavior from this. Whether you can prove this or not, but you can kind of test this, whether the amount of electric charge stopped is different from the amount of baryon charge. And this is where, let me skip this. This is why isobars help. We measure the amount of charge stopped, electric charge that is stopped, and measure the amount of baryon that is stopped, and we compare them. If this is greater than this, then same object is carrying the both. If it is the other way around, then something else may be carrying, or the flow of the baryon number is through something else. And the reason it's done through isobar is because isobars are 2 species where the baryon numbers are same, but a little bit of electric charge difference, because the electric charge is different in these 2, they can be very precisely measured. Why? Because we did this, right? We made the experiment in such a way that anything we measure in ruthenium or zirconium will be measured with very good precision. So here is a measurement of charged particles with very high precision, and this is done, and we are, right now we don't have the results, but this is going to be coming up very soon from start. Okay, so that's pretty much it. I kind of told you that isobar collisions opened up a path for precision measurement. The idea was basically to start the magnetic field driven effect, but there was a lot of this kind of came as a byproduct that you understood nuclear structure, and then the main goal, the chiral magnetic effect charge was pinned down, And now we have new exciting opportunity to understand baryons. So it was a success, and I hope it gives you an introduction to the following discussions that will be in the course. So thank you.
5 minutes for questions.
Yeah, so this first part of your talk, you're talking about the problems, you didn't understand the geometry of these two nuclei. And that sort of relies on the picture that the nucleus density distribution is frozen. But actually it's not. You know, you have a 0-point motion on the nuclear surface. And that was introduced years ago to describe the subbarrier fusion. So if you have different monopole moments or different vibration, low energy vibrations that are monopole vibrations of the same, they don't need to be the same for the thing they're called. I don't know if this is of the order of the magnitude that you're talking about here, but that's just a piece of structure physics that you haven't taken to talk about.
Yeah, I mean, I think this is based on the fact that in the time scales of our relativistic heavy collisions, if this is frozen to a particular kind of configuration, and then the fact that in the most violent collisions, the geometry, you have mostly like a geometry dominated anisotropy that we measure, that will be different between the two species. But we could go on few more rounds of sophistication and kind of probe a little bit deeper into what's going on. So this is one of the measurements, but we are trying to perform more. There's also, I mean, there will be more discussion of how even, but this is not the first time though we see this. We did uranium also, collided uranium at RHIC, and also gold ion. There we also saw differences. So I think that probably is a topic of discussion.
Yeah, so deserve maybe more discussion. Just a little bit because I will write it down. Okay? Yeah.
So, in my understanding is that because they have the same number of mass numbers, so that they have the same strong interaction, then the difference in the multiplicity will come from only the electro-magnetic interaction. Then how can you plot the neutron spin in this study?
You know, the fact that, it's not from the electromagnetic interaction. It's from the fact that this is more diffused object. So the energy density is diffused, distributed over a wider surface area. So the kind of, you could think of like how hot it becomes, like the mean PT is related to like the temperature. So this is a little bit more denser system than this, because just the energy density is distributed over wider region. It's not electromagnetic.
Yeah, I was curious for the multiplicity results that you're comparing there. You said you're doing Glauber. Do you know if someone's done that with a hydrocode? Because we've compared like the initial state distribution to with and without hydro, and there are slightly different in the tails of the distribution. So I was curious if someone had done that.
Yeah, I mean, I think this one we haven't done with hydro, but I think we could do this with, I don't know, we did it with Trentro. Oh, okay, I think, oh, well, okay, yeah, of course.